From the raging infernos that consume forests to the seismic tremors that reshape landscapes, natural disasters are a stark reminder of Earth's formidable power. Annually, these events claim countless lives, displace millions, and inflict billions in economic damage. The human toll, however, extends far beyond statistics. It's the loss of homes, livelihoods, and the very fabric of communities. For centuries, humanity has largely reacted to these catastrophes. We've rebuilt, responded, and recovered. But what if we could peer into the future? What if we could anticipate the next flood, the upcoming drought, or the impending wildfire with enough lead time to make a tangible difference? The traditional approach to disaster management, while critical, often begins after an event has struck. This reactive stance leads to delays in aid, challenges in evacuation, and ultimately, greater suffering. Imagine the difference a few hours, or even days, could make in moving populations, securing infrastructure, and preparing emergency services. The imperative, therefore, is clear. We must shift from reaction to prediction. Enter the era of predictive systems, a revolutionary leap forward powered by cutting-edge technology. These systems are not merely guessing, they are analyzing, learning, and forecasting with an unprecedented degree of accuracy, giving us precious time back. So, how do these sophisticated systems work? At their core, predictive disaster systems are colossal data engines. They ingest and analyze vast datasets from a multitude of sources: real-time satellite imagery tracking atmospheric conditions and land use changes, ground-based sensors monitoring seismic activity, soil moisture, and river levels, ocean buoys detecting tsunamis, and even historical disaster data spanning decades. Weather stations contribute atmospheric pressure, temperature, and wind data. This raw, complex data is then fed into advanced artificial intelligence, AI, and machine learning, ML, algorithms. These algorithms identify subtle patterns, correlations, and anomalies that human eyes might miss. For instance, ML models can predict the trajectory and intensity of hurricanes by analyzing atmospheric pressure, temperature, and wind shear patterns. AI can forecast wildfire risks by combining data on vegetation dryness, wind speed, topography, and historical ignition points. For floods, models integrate rainfall forecasts, river levels, and terrain elevation to predict inundation zones. The more data they process, the smarter and more accurate they become, learning from past events to refine future predictions. The applications of these systems are truly transformative. Imagine receiving an alert days before a major flood, allowing communities to evacuate safely, move livestock, and businesses to secure their assets. Think of authorities precisely allocating emergency resources, where to position rescue teams, where to send medical supplies, how to manage logistics, based on predicted impact zones, rather than reacting blindly. In wildfire management, predictive models allow firefighters to create fire breaks proactively and deploy resources strategically, potentially containing blazes before they escalate into uncontrollable infernos. For earthquakes, while precise timing remains elusive, AI is helping us understand fault line stresses and identify regions at higher risk, leading to better building codes, infrastructure resilience, and preparedness plans. These systems are not just about predicting the weather. They're about predicting the impact of the weather and geological events on human lives and infrastructure, enabling targeted, life-saving interventions. Despite their immense promise, predictive systems face challenges. Data quality and interoperability between different international systems are significant hurdles. The sheer computational power required for real-time analysis of petabytes of data is another. Ethical considerations, such as data privacy, ensuring equitable access to early warnings, and preventing misuse of predictive insights, also demand careful navigation. The black box nature of some AI models means understanding why a prediction is made can sometimes be difficult, necessitating explainable AI research. However, the future is bright. Continuous advancements in sensor technology, satellite networks, quantum computing, and global data sharing initiatives are pushing the boundaries of what's possible. International collaboration is crucial for building a global network of predictive intelligence, transcending geographical and political boundaries. These systems offer us a powerful tool to mitigate the devastation of natural disasters, but they are only as effective as our willingness to invest in them, trust their insights, and act upon their warnings. By embracing predictive technology, we're not just preparing for the future, we're actively shaping a safer, more resilient world for everyone. Join the conversation. How do you see predictive systems changing our relationship with natural forces? Share your thoughts in the comments below.